Hello. In this video, I'll introduce the simparm.grg parameter file. This parameter file is common to all of the tools in the LRange modeling family. It's the parameter file that informs how a simulation should find the information that it needs, plus a few parameters, like the length of a simulation, for example. And so it's really a controlling parameter set, controlling the nature of the simulation. So I'll mention this again, but for example, because it's pointing to the source of different kinds of information, it's a common file to edit when doing scenarios. So if you run a simulation with the files being pointed to being some baseline, say, you'd be able to store that result, and then you can modify the data in question for whatever scenario may be of interest, and then edit simparm to point to the new location, run the simulation again, and that would be a scenario that could then be compared to the baseline and differences discussed. Again, I'll go through it line by line. You'll have a good sense of how this works. Let me first show you that this is really the bulk of the simparm file. There are just a few lines at the bottom not shown. For now, though, I will zoom in, and I think in this case, we will let the outline go and expand the image. And so onward. At the top of the file, you see a few choices that control how a simulation behaves. These aren't things I've changed. I haven't changed them in a long time, but they were put in place for software development and can still be used today. When the software is running, there's an echo file produced. If there are any issues, if things just aren't coming in correctly, or if things seem to be behaving strangely, an analyst can look at that echo file. It's just echoing inputs. And so an analyst can look at that echo file and work to figure out what might be going on. That first choice is turning on or off the production of maps, the spatial maps that are being read in. There are many of them, and so having the option to turn that off would save space and time and such writing to that echo file, but it's really a minor effect, and so I've left it to true for a long time now. The echo to screen level is the same. It can change how much information is printed to the screen that a person doesn't need, but if you want a verbose simulation that shows more detail about what's happening, you can turn that to a 1 or the like, and it will produce more information. I haven't used that in some time as well. The map files is just a string that helps to identify the next section. And then on to the information being provided to the software. And you'll see an example or two of kind of legacy effects, files that might be put in place but they're not used. That is included in the first 4. So we have our first 4 entries there. Zone, you'll see that each of these entries, they're grid ASCII files, which is a spatial format. I'll talk more about that in another video, but the zone is, I should say you'll see as well that these are at 0.5 spatial resolution. So these are the images from the initial GRange application, which was at ½ degree resolution. That's the resolution of the simulation discussed in Boone et al. 2018. Onward then, I keep starting and stopping. For the zone file, this is pointing to a layer within the layers folder. Zone 0.5.ASCII is talking about giving a unique value to every cell in the landscape. So the landscape, in this case the entire world, is divided into pixels, cells, and every cell gets a unique identifier. Those identifiers are called zones. And so there are means to create that file, but basically, I'll talk about in another video, but basically that's a layer that you'd be unlikely to change, and includes a unique identifier, literally just 1, 2, 3, 4, 5, up to some large number that uniquely numbers each cell in the landscape, whether it's ocean or land or what have you. The next layer is land 0.5.ASCII. And this isn't used directly in modeling. This is used instead in outputting some surfaces. So not really part of the processes that are simulating ecosystem dynamics, but rather used in outputting spatial surfaces so that the model is able to output spatial data that can be used by a graphical user interface that shows the ocean and the land. No matter if you've only simulated rangelands, as is typically the case with this tool, you just don't want those rangelands floating in space. If you can see the oceans in place and the continents in place and the rangelands laid over the top of them, things make more sense. And that land spatial surface helps to do that. I spoke of some legacy effects. Elevation is the next layer. Typical elevation coming from the shuttle rain radar topography mission or other sources. That's not used in modeling directly. It's remained, I've left it there, but it's not used right now in modeling directly. LATS is latitudes. And so LATS 0.5.ASCII is the latitude of the center of each cell. And so they're the same value across the map, but as you move up or down the map, the values change, and they are real latitudes. What those represent then are a means for the G-Range software to calculate day length. That's how the model is able to calculate day length, which in turn informs seasonality, phenology, but primarily solar insolation, how much sunlight falls in a given place. And so those first four layers are, with the exception of the one that's not used, are informing the model either in a critical way for zones or for latitudes, or through the graphical user interface for the land layer, for example. The next 12 surfaces are related to soils. And so you can see two groups. One is for topsoil, one is for subsoil. So there are 6 layers that inform topsoil, again, grid ASCII layers. These were all developed from the Global Harmonized Soils database. And in that database, there's a designation for the topsoil and subsoil, the difference at 60 centimeters, or I don't recall anymore. That certainly wouldn't be the case. That's too deep. Please look at the manual to know what's topsoil and subsoil. And those definitions can be changed, of course. But in the Harmonized Soils database, you see the 6 layers that are indicated, and they're used in both Century, the underlying biogeochemical tool that informs G-Range, and G-Range as well, to infer things like the initial carbon pools and the nature of water flow through soils. And so you can see that the first 3 are traditional soil texture layers. So we have percent sand, percent silt, percent clay. We also have percent gravel, which would be above some cutoff in terms of particle size. The last 2 entries are bulk density and carbon in the soil. And so those 6 parameters are provided for the topsoil, and then 6 as well for the subsoil. Please see the citations and user manual for the units that are used. The next is, I don't recall what the ST10 is about. Again, I think these are gently modified copies of the original G-Range source. And perhaps colleagues did that, or I did. But the next 2 layers, well, really the next 4 layers, are about vegetation cover. And so you see tree cover represented in the next 2 layers. The deciduous tree cover is shown, and that's percent cover, 0.5. So we have deciduous percent cover at half-degree resolution and evergreen percent cover at half-degree resolution. And so together, those capture total tree cover for the globe, in this case, locally for L-range. The next is shrub cover. So SHB adjusted. Why it was adjusted, I don't recall, but that's shrub cover. And so this is, again, perfectly appropriate to update the application. It's not a trivial exercise, if you wish, but the shrub layer that was used in the original G-Range application has the sources have certainly improved in the decades since that was done. Copernicus, for example, that program has much better information on shrub cover. And so it would be worthwhile to update, but then the product does need to be assessed again. The next is herbaceous cover. And so we have herbaceous cover, HRB adjusted in this case, shrub cover, evergreen tree cover, and deciduous tree cover. Again, those are percent covers. There's no bare ground in forming the model. Those values are subtracted from 1 to yield an estimate of bare ground. And again, I hope you get a sense that these can be changed. They can be updated. Improved data sets can replace those. As soon as there's a change, the model should be rerun multiple times, compared to observed data to make sure that it continues to behave well, and adjustments made to make sure that it does continue to serve the modeler's purpose. But they can be altered. They could also be altered to support scenarios. So if you were interested in changing tree cover as part of strategic goals, for example, then you could increase the tree cover in the deciduous and evergreen layers and simulate the effects of that on various aspects of the ecosystem. The next layer, which is the SAGE layer, that's actually referencing a biome map. And so again, this is from the original G-Range application. I used a SAGE biome map, which divided the world into 15 land cover types, landscape units for my purpose. It was 15 biomes, and I labeled each biome a different landscape unit. Landscape unit in this case being the areas considered sufficiently homogeneous that they would have one parameter set provided for them. Now, that name, again, is going to vary in different applications. Certainly in a local application, it would have a different name. Whatever you happen to decide would be your land cover units, landscape units. In Africa, it has a different name. But the logic, if you will, is the same. It's the spatial map that's dividing the area being simulated into sufficiently homogeneous units so that sets of parameters could be provided. So as you'll learn in the accompanying landscape unit file, there are sets of parameters that match the designation in the SAGE file. So again, if you wish to have different landscape units represented, you would change this map, you would change the landscape unit map, or parameter file rather, and you'd be on your way. Again, it would be a change that would require running the model, assessing the model, making sure that it was behaving reasonably before use in discovery. So we have two main maps, if you will. I'll talk about this again when speaking of spatial data, but we have two main maps, two main almost land cover maps or landscape maps that are used in G-Range and L-Range. The first is this landscape units, which is shown at the top of the screen here. In this case, it's the SAGE biome map. And so that's breaking the landscape into landscape units. The second one, so it's kind of a heavy lift, if you will. It's got a big job telling the software which pixels belong to which landscape unit. The next map is, again, just a spatial map, but it's got a much smaller job. It is a land cover map, and its job is to allow for areas to be modeled or not modeled. And so even within a given landscape unit, you can turn on or off areas, whether you want them modeled or not. In this case, the Goji database is it's part of the seasonal land cover database, and it's very detailed with 99 land cover types for the globe. I chose that because of those 99 types, and they allowed me to have more control over patches that were going to be simulated or not. And so you'll see when I review the goji.legend file, the way that those can be turned on and off. And so that file then allows me, that spatial map informs the program which land cover types belong to each pixel, and or type perhaps. And then there's a legend file that follows, the Goji legend. Again, it could have a very different name in the application you're using, but that then allows the individual land cover types to be turned on and off. So if you're not interested in modeling urban areas, as you may not be, you can turn those off. If you're not interested in modeling barren or snowfields, you can turn those off. In contrast, in the African application, I wanted to do the whole continent and let the differences in land cover and their appropriateness for simulation kind of settle out in the post-hoc analyses. And so all of the land cover types are turned on in that application. The entire continent is simulated. The next two lines relate to precipitation averages, temperature averages. These are used in fairly subtle ways within the Century model logic, and so they are spatial data. They represent long-term averages, both for precipitation and temperature. They are used in processing the aspects of the biogeochemistry of the model. I don't imagine changing those as part of a scenario, although they could be changed if one was to be ultra faithful to a given climate scenario. The next layer is a little more complex. The next set, rather, of layers is a little more complex, and it's the prefix to the climate parameter sets. So they live in folders. They live in either the same or different folders. In this case, they're in 3 separate folders. You can see the first entry. Let me move it to the top. Well, near the top. And you can see the first entry, it ends in /P. That is the folder. Actually, the precipitation folder precedes that. So you can see this is using a given global circulation model. It looks like it might be from the Hadley group. And so it is for RCP 8.5, if you're familiar with that. There's precipitation, and then each file within that collection begins with P because it's for precipitation. The next entry is from the same data set, and it begins with X for temperature maximum. So as you might guess from the folder name, it is the maximum temperature for the given month. The next is the minimum temperature for the given month. And again, those files will start with N. Those for maximum will start with X. And so these three lines are commonly edited when doing climate scenario analyses. If you're interested in a baseline, you'd edit to point to a given set of data. If you want to run the estimates from a given global circulation model, you would edit to point to those data. And so often these three lines get edited to capture a climate scenario. The next line, which is underscore 0.5.ASCII, is accompanying those previous lines. It's what allows the software to generate a file name. So most of these files are just given to the software and it uses them directly. But for the climate data, there are hundreds or thousands of surfaces. And so instead of doing that, they're all named in a predictable way. And the software actually creates that name on a fly based on the year in question and the month in question. And then it needs to know how that file ends. That's indicated in this line with the suffix. So I know from looking at this that the precipitation, say, will live in this precipitation folder. It will begin with the letter P. It will have the year and the month, probably with an underscore in it. But we can look at the format of that to confirm. And then it will end in underscore 0.5 or 0p5.asc. And so the software is creating that name on the fly. The next entry, as you might guess, is pointing to the landscape units file. This is the main parameter file describing how vegetation grows. Again, the name. So some of the files used in GRange and LRange are hardwired, as we say in computer science, where like the simparm.grg file, it has to be named that. If it's not there, the software is not going to run. The same isn't true for landscape units. You can call it what you wish and edit what you call it in this file. So again, I may have a baseline simulation that has values stored in landunits.grg, and I may have another that's named land units twice CO2.grg, and then I can run one simulation for a baseline, or perhaps many, to get standard errors and such, and then I can edit the simparm.grg file, this file, to point to that twice CO2 landscape units file, and then run more scenarios capturing that scenario. The next entry is for fire. And if you have it set at 0, fires are going to be managed probabilistically, meaning that there is a map that will be used to inform probabilities of fire burning. If you set it to 1, then you're asking the software to use the fire.grg file to schedule burns. So you'll be able to have very fine control over areas that burn and where they burn, when they burn. And so you can have ultimate control over what was going on each month in that regard. So here it's set to 0, meaning that the fire.dat.grg is not going to be used, and instead the probabilistic fire will be used, the one that's pointed to. The same kind of pattern is used for fertilization, and so it can be probabilistic, it can use maps, and so probabilistic can be turned off. Fertilization has not been used in earnest by most people, and so it requires some care to enable that, but the software has been created to allow that management practice to be represented. The next entry is the CO2 concentration. It's really, nowhere does the software learn what the actual CO2 concentration is. Instead, it's informing a correction factor to productivity. So by default, it starts at 80%, and that is kept constant through time in the CO2 file that is being pointed to by simparm.grg. In this case, it has an increasing rate of productivity associated with increasing CO2 concentrations with RCP 8.5. The next variable is whether to use a state variable model, to do nothing, to write out a new one, or to both read one and write one. And so state variable files are basically files that are created to allow the software to essentially start after a long simulation at each run. So if I wished, I could set that state variable treatment to 0, and it would just ignore a state variable file. It simply start the software and run for however many years I have requested, and things happen normally. But you can have a lot of noise early on as, for example, the carbon pools in Century become more stable, balance out, as vegetation dynamics balance out. And so people often will do a spin-up of a simulation where they let it run for some time, let those pools and dynamics settle down, and then write the state of the simulation out at the end. That's done by entering a 1 in this variable, state variable treatment. Again, these comments continue to the right, as you might guess, and give more detail. So if you turn that to 1, it will write out a state variable file at the end of a simulation. And then when you run the model next time, you can take that name, that file stored in the output folder, copy it over to an input. That's just done to avoid overwriting something accidentally. So you have to literally go in and copy it, but just the one time. And then you can change the state variable treatment to 2, and then it will read that file at the start of every simulation, and it's as if the simulation has run for some number of years, even though it's starting immediately. It's as if it has run some number of years and the carbon pools and such have balanced out. And so by using a spin-up file, you can avoid that early bouncing around and non-stable dynamics that we see in early simulations. You may not avoid it completely. There still may be some odd behaviors, but they tend to dampen very quickly and become more reasonable very quickly with the use of a state variable file. And so it's as if you had started the model after many years of simulation. To give you a sense, in Century, they do typically a 2,000-year spin-up to allow carbon pools to stabilize. And I've done the same in GRange. The last two parameters are straightforward. They are the year to start a simulation and the year to end a simulation. And so in this case, you see that the simulation is very brief, just 5 years, starting in 2001, ending in 2005. And there's a reminder at the bottom not to edit this file beyond file names and the like. If you add or remove lines, you'd likely break the software.